Everybody, welcome back to our afternoon session. In the last session of today, now we are going to have a talk in the software track called A Beginner's Guide to GPU for Pythonista from the speaker Marlene, who is the current vice chair of the Python Software Foundation, the chair of the PyCon Africa, co-founder of SimplePy, a non-profit organization that gives Zimbabwean women access to resources in technology. And she is now currently studying computer science in the University of London, as well as interning in NVIDIA. So without further ado, we can invite Marlene to give her talk.
Hi everyone, my name is Marlene, and I'm super excited to be with you right now for PyCon Sweden 2020. And I'm a little sad that I couldn't be there in person, but also very grateful that I can join you remotely. So the title of my talk today is A Beginner's Guide to GPUs for Pythonistas. Before I get started, a little bit more about myself. I am a director and the current vice chair for the Python Software Foundation Board of Directors. And for those of you that don't know what the PSF is, the PSF is the nonprofit organization behind Python. And if you'd like to learn more about what the PSF does or become a member, you can visit python.org and click the PSF tab. Something else about myself is that I am current chair of PyCon Africa, which is the Pan-African annual gathering of the Python community on the continent of Africa. We had our first conference last year in Accra, Ghana. It was really fun and very cool. We also had a conference this year remotely, and hoping that next year we'll be also able to have a conference in person. So if you're interested in finding out more or maybe joining us next year, feel free to visit pycon.africa for more information. And then a final thing about myself is that I am currently interning with the Rapids team at NVIDIA, and I've really enjoyed working with the team there for the past few months. I've been working with GPUs and Python, and it's been really interesting and challenging and quite a big motivation for why I decided to give this talk as well. So let's get into it. So the first thing that I think is important is for us to understand why Pythonistas should be interested in GPUs in the first place. Typically, when people think about GPUs, I know for myself, when I first started looking into this topic, people associate GPUs with graphics cards and gaming. And oftentimes people get surprised to find out that GPUs can be used for anything outside of the gaming world. And this assumption, to be fair, is fairly accurate. If we actually do a quick search on Wikipedia, which as many of us know is the source of all truth, we actually discover that GPU stands for Graphics Processing Unit. And the original purpose of the GPU was to create images for computer graphics and video game consoles. So the common assumption that I had, and I think many people still have to this day, is fairly accurate. However, since the early 2010s, we saw a sharp rise in the use of GPUs, or general purpose graphics processing units. So as you can imagine, general purpose GPUs are GPUs that can be used for more general purposes. So typically, these sorts of GPUs are used instead of a CPU for executing tasks that can be run in parallel simultaneously. And they're usually known for speeding up your workflows. So, a good way that we can kind of help visualize what this means is to think about coffee. So one of my favorite things that I love about conferences being remote these days is that I don't have to wait in line to get a cup of coffee. Literally this morning, I just woke up, went to my kitchen, poured myself a glass, and my coffee is down there. Anyway, I have my coffee with me. It's incredible. But sometimes, not all the time, but sometimes when you go to in-person conferences, there are these really long lines leading to one coffee machine. And this can be really frustrating, especially if you want to go and watch other talks or give your own talks. But here you are, waiting in a line, waiting for coffee. So one solution to this problem is just to add an extra coffee machine. And this allows things to move a lot faster because the queue gets basically cut into half, and people can easily access their coffee, grab it, and go ahead and do other things that make them more productive. So we can think of the cores in our computers like these coffee machines, in many cases utilizing actually the more cores on our computer can make us more productive in the work that we do. So typically a CPU has anywhere from between 4 to 8 cores, whereas a GPU can contain thousands of them. And having a higher number of cores increases our computational power. And in some cases, specifically when you're able to run tasks in parallel, it makes us be able to do more work faster. So I do want to give a quick disclaimer here, especially for the CPU lovers that are about to send me nasty emails, that I do still think, CPUs are very important. There are some tasks that CPUs are much better suited for than GPUs. Say, for example, if you have a task that requires a lot of serial processing, where you're processing things one by one in a specific sequence, then in these cases, it's best to use a CPU. And by the way, even if you're using a CPU, you can take advantage of those 4 to 8 cores on your laptop by using things like multi-threading or async IO, all of the buzzwords associated with concurrency these days, to boost your performance and get better speed for your Python code. So since this is a beginner's guide, I think something people might be thinking right now is, Marlene, you're talking a lot about speeding up Python and getting better performance, but I've been using Python for quite a while now, and it seems pretty fast to me. I can do my calculations and it's fine. I don't see it as slow. And this is a good question to be thinking about. A good follow-up question as well to ask is Python slow? And this is quite, believe it or not, it's quite a contentious topic in the community and in parts of the community, I would say. And when I looked online for answers to this question, I found a lot of different opinions about it, and some of the opinions were really helpful. Some of them were very unhelpful and borderline slander, I would say. But I came to the conclusion that the slowness of Python is fairly relative, and many developers will likely never encounter this slowness that people talk about. But there are some cases where this is true, and I do think it's important that when we talk about Python being slow, we understand what we're comparing it to and when. So earlier this year, Anthony Shaw gave a talk at PyCon US, and his talk was called "Why is Python Slow?" And basically the talk was just answering that question. And at the beginning of this talk, he presented a really cool benchmark where Python 3, CPython, which is the version of Python that we download from python.org, he compared that version of Python to several other versions of several other languages for computing the n-body algorithm. And so the n-body algorithm is a program that models the orbits of Jupiter, Saturn, Uranus, and Neptune. And as you can see from the chart, Python is not doing so great in terms of speed compared to other languages. And for some perspective, the Python interpreter is written and compiled in C. But if you compare its execution time to that of C when computing this algorithm, C takes 7 seconds and Python takes 14 minutes. That's just really different. And Python is really slow compared to C in this case. And even when you compare it to other languages like Node.js, which is also dynamically typed, and not strongly typed like C, Node.js is a lot faster than Python. And I'm not going to go into the details for this. If you would like to know specifically why Python is slow in those cases, feel free to watch Anthony's talk. It's a great talk. I will side note here and say quickly that even though in these cases Python is slower than these other languages, it is actually much more popular than all of the languages that are faster than it in this chart. And I think that's just a testament to how much people enjoy using Python and how easy and intuitive it is to use. And so there is a lot of benefit, I would say, to trying to put effort into figuring out how to speed it up. Okay, so I talked earlier about how utilizing more cores in our computer can make us have, can speed up our workflows and make us more productive in the work that we do. And we can do this through things like concurrency and multi-threading. However, in the past, Python actually hasn't had a very friendly reputation with multi-threading and parallelism because of something called the Gill. So Python's Gill has a very strong and well-known reputation. Actually, if you do a search on YouTube for Python talks on the Gill, I did it and I got this very strange mix of suggestions. So Larry Hastings has a couple of videos where he's explaining this project called the Gillectomy, where he's literally trying to take out the Gill from Python. Dave Beasley, who's a really smart guy, I follow Dave on Twitter, is trying to understand the Gill, and he carries out several experiments, just trying to see what happens in different situations with and without the Gill. And then Eric Snow, who is a Python core developer, is trying to decide whether to Gill or not to Gill. It's just, as you can tell, it just has a very strong reputation. It's just a lot going on with the Gill. And I'm just like, okay, what is actually going on with Python's Gill? So the Gill is Python's global interpreter lock. And it's a lock in CPython that preserves its internal shared global state. And sometimes the Gill can be considered occasionally controversial because of it, not more than one thread can run in Python at a time. And for people wanting to utilize multi-threading and running many different threads at the same time to speed up their work, the Gill can sometimes stand in their way. However, over the past few years, the Gill has become less and less of a barrier for speeding up Python in this respect. GPUs are actually only one of a number of different ways to get around this problem and still do things like multi-threading to be able to speed up your code. I watched a talk, Raymond Hittinger's 2017 keynote on concurrency at PyBay, and this specific clip I found very helpful in terms of understanding why the Gill is important and some different ways we can go ahead and get around it to be able to continue doing our work and doing things like multi-threading and concurrency. So here it is.
My friend Larry Hastings is working on a project called the Gillectomy to remove the global interpreter lock from Python. Do you think that's a difficult project? That is an incorrect hypothesis. It takes about a day of work to remove the Gill. He removed the Gill on the first day. It was no problem taking it out. The problem then becomes all of the locks that you have to put in everywhere else in order to get Python to function. It turns out that's not particularly hard either, and a few days later, he had that done. So the Gill is gone and replaced by lots of other little locks on smaller data structures. Problem solved. Any questions? Oh, are locks expensive to acquire and release? In fact, they are. And so the good news is the Gill is gone, it's free threaded, and it's dozens of times slower than regular Python. So you actually get a payoff for the Gill. And the payoff is you don't pay all of the performance cost of all of these individual lock acquires and releases. It's actually a really nice thing to have. It gets in the way of us free threading, but we have ways of solving that problem. If you can't fully free thread one Python, why don't I run 8 Pythons in parallel, each with their own threads? And then it's no problem. I'm taking advantage of all of the cores. Or you can combine threading and multiprocessing. There's a number of ways to go. In fact, at some point, most folks just get over that Python has a global interpreter lock, go ahead and saturate all 8 cores to 100% and get full advantage of the machine and just simply ignore the problem. There's lots of ways to ignore the global interpreter lock.
Like Raymond said, when we utilize all the cores of our computer, we don't really need to worry about the Gill. And with GPUs, we have thousands of cores. So if we decide that we wanted to run one version of Python on each core and use one thread, we would still get a really significant speed up. Okay, so now that we've looked at some of the performance issues that we might run into that would lead us to using a GPU, let's look at some practical examples of how and when it's useful to use them. Data science is a really important field, and it's probably the main field where GPUs and Python are being used together. Modern data sets these days can contain millions, even billions of data points, and usually these data points need to be processed. For data scientists that are looking to process their information using Python, simply using plain Python can be really efficient. And data scientists can find themselves, just like in the coffee example, just waiting for Python to process their information and honestly just wasting time and being inefficient and not productive. Recently, there have been a number of libraries that have been created in order to speed up Python code to be able to process these large amounts of data. One of the most popular libraries that have been created is Pandas. Pandas isn't a GPU-based library, but it does use vectorized operations to run functions at really high speeds. And because of it, it does make a significant speed up from just using plain Python. So before we actually move on to the GPU part of this, I think it's important. I want to give an example of how much of a speed up we get simply by switching to Pandas. So let's take a look at some code.
So at the moment, we are starting off on Google Colab, and this specifically for context is the Rapids notebook. Rapids has a really great free notebook on, if you just go to the Get Started page, you can have access to this notebook, and basically it allows you to test out a GPU and the different Rapids libraries very quickly, and we'll just walk you through some of the basics of that. We are not yet starting off with our GPU, but just to give you some extra context, at the moment we are importing our libraries, and then we're creating some data using NumPy, some random data, and then we're going to start off by creating a pandas data frame. And this is, a very simple way to do it. And then after we create this data frame, we're going to see how long it takes using the time module. We're going to see how long it takes for pandas to calculate the mean of the data in this column. Okay, so I'm just going to go ahead and do that. I'm going to create a separate column in the pandas data frame, and I'm going to go ahead and use the pandas rolling method to calculate the mean. And this is a great method that really speeds things up. Yeah, so let's go ahead and see how long it takes for pandas to calculate the mean. Oh, that was really quick. And it takes about 0.03 seconds, as you can see there, which is really fast. Now, the next thing we're going to do is we're going to figure out how long it's going to take for Python to do the same thing. And instead of using the Python rolling method, we're going to create, as I'm doing now, we are going to create a for loop. And basically what this for loop is going to do is we're going to use the mean loop column in the data frame, and we are going to just loop through all of the values and calculate their means and add them to the data frame as well. But this time, of course, using Python and not pandas. So as you can guess, this is probably going to be longer. We're going to just going to fill this up, but we're going to, we're going to calculate this and also time it and see how long it's going to take for all of these loops to run. Let's just comment out that code and let's run it to see how long that's going to take. So the loop here using Python looping over took a full 1 second and 16 seconds. Let's just do with both. That's a lot. That's a big difference. That's a really significant difference. And this is even using the CPUs from Google, which are really fast.
We can get pretty significant speed ups just from switching to the Pandas data frame library. And believe it or not, using a GPU can push this even further and give us much better speed and much better performance. So like I mentioned earlier, I've been working with the Rapids team at NVIDIA, and specifically I've been working on the cuDF project. And so cuDF is a GPU Python-based data frame library, and basically what cuDF does is that it mirrors the Pandas API. So for data scientists, almost everything that you can do with Pandas, you should be able to do with cuDF. But what cuDF does is that it performs all the computations on the GPU, so it speeds it up significantly. The nice thing is also that it's a drop-in replacement, so a lot of the methods and things like that are really similar, and so it's not really difficult to learn. Let's take a look at an example.
Right. So here we would like to compare Pandas and cuDF and see the difference in speed. For this, we're going to be using TimeIt to just see how long it takes for Pandas to do some calculations and how long it takes for cuDF to do calculations. So as you can see, right now at the top, we are creating a Pandas data frame, and this data frame has significantly more data than last time. And then I want to show just how easy it is to convert a Pandas data frame to cuDF. And it's a very similar instruction, and then you're using the method from Pandas and just putting in your original Pandas data frame. You can also create your own cuDF data frames from scratch if you'd like to as well. And so we are going to start off by using Pandas to calculate the mean of the data that is in our Pandas data frame. And we're going to do the same thing as well with cuDF, and we're going to time both of these operations and see how long it takes to do this with Pandas, and then to see how long it takes to do this with cuDF. So just finishing that up, and let's go ahead and run this and see what the time takes. Hopefully it doesn't take too long. If it doesn't, I'm just going to cut this video and we're going to speed through to the end. Okay, there we go. So it takes, that's great. It takes about 156 milliseconds per loop for Pandas and 3.56 milliseconds per loop for cuDF, which is really significant. So I did want to also show you a second calculation, which is just merging data together. And I ran out of RAM to do this on Google Colab because it is a much larger computation to do. And so instead of trying to do it here, we're just going to move over to a Jupyter notebook that is using my own local GPU. So here we are in our Jupyter notebook, and behind the scenes we are running a GPU, so we are still able to access our cuDF GPU data frame. We have a similar setup from what we had last time. We're importing our libraries and creating the same data frame with Pandas. But this time we're trying to merge the data together, at first with Pandas and then with cuDF. So I'm just running that. And yeah, so I had to, this took quite a long time to run, particularly with Pandas. So I had to speed things up. So I'm just going to jump forward a little bit. All right, so it did take quite a long time to get through the the calculation. With pandas, I actually cut out a whole section of time. And here, pandas, to go through all of it, took about 1 minute, 10 seconds, plus or minus 486 milliseconds per loop, which is quite a lot of time to go through all of those loops. It was a lot of data, so pandas was quite slow. But next, we can just let it go through and calculate. And as you can see, for QDF, it was much faster. It took about 367 milliseconds to calculate that per loop, which is a lot faster.
So as you can see, again, we get really significant speed ups from pandas. And obviously from Python, it's I don't know how many times faster. And this is really great and can be helpful, especially for data scientists that are dealing with very large data sets. In fact, the larger the data sets, the greater the speed ups that you will get from QDF. And for me, it's been really interesting. I had come from a more of a web developer kind of background. I'd done a lot of work with Django before with Python. And so crossing over now and doing like building features and fixing bugs for a performance-based library has been really interesting. I think it's been sometimes challenging, kind of getting into the mindset of thinking about, okay, how can I make sure that I'm keeping the computations on the GPU, and how can I make sure that my algorithms are as performant as possible? And it's been really interesting learning from that. Right now, I'm working on an interval data type that we will be adding soon to QDF. I've also added a couple of features and things like that. So it's been very fun. If you're interested actually in contributing to QDF, feel free to message me and let me know. It's an open source project, so we're always happy to be working with people. Okay, so a couple of other fields that people are using Python and GPUs, mathematics, not just with data science, but as a whole is quite a large field where people are utilizing GPUs. Data visualizations is another field. Machine learning and AI has these days, almost exclusively, machine learning models are trained using GPUs. So for anyone wondering how they can get started using GPUs and maybe trying it out, almost every major cloud provider, whether it's Google Cloud or Amazon Lambda, gives you an option to be able to access a GPU online for a minimal cost. So thank you so much. That is going to be it for me. I think I will be doing a live Q&A session after this. Please do not ask me very complicated questions. As I said, this is a beginner's guide because I am basically a beginner to this field, I would say. But if you have questions, feel free to stay after, where I'll be doing a question and answer session live, or feel free to reach out to me on my Twitter, which is Marlene_ZW. But thank you so much for listening. Bye.
So thanks a lot for the very interesting talk. So now we go to the Q&A. There's some delay on YouTube, so we can wait a bit. But in the meanwhile, I have one question. So in the talk, you talked about this project on data frame, so on QDF. So how would it compare to other data container formats in Python? For example, CuPy that implements NumPy like arrays. You're muted. Yep.
I'm muted.
Yep.
Can you hear me now?
Yes.
Okay. I'm actually not like super sure because I haven't used CuPy myself.
I wouldn't be able to say how it compares because I've actually never compared the two together. But mainly, I would say how similar. I would think through. Okay, how similar is PyPy to pandas? Is it very similar to pandas? Do you know? I wouldn't know.
NumPy.
Oh, it's a NumPy. Okay,
Yeah.
I don't know actually. I haven't tried it out, so
Yeah.
I will have to do that and get back to you.
Yes. No problem, no problem. So yeah, so overall, I think it's a very interesting talk. So if there are no more questions, I see. So we can end the talk here and we can go to the next talk. So
Okay.
again, thank you very much for today.
Thank you so